So the discovery of fusion. In the mid-1930s, Enrico Fermi was trying to make a new element. And he did this by bombarding uranium with neutrons. The theory was that if he could get a neutron to stick in the nucleus, you could maybe, it might undergo beta decay and convert that neutron into a proton. I mean, you kind of wonder, how do you even come up with an idea like that? But so he did detect beta emission. So he's throwing an electron at uranium atoms, and beta emission is electrons coming out, right? So something was happening, but he never examined the products to see exactly what they were, so he didn't know if a new element had actually been formed. But that was one of the first experiments with fission. Other scientists repeated his experiments, Lisa Meitner, Fritz Strassmann, Otto Hahn. They found that the products contained several elements that were lighter than uranium. And that was a discovery that changed the world. So in 1939, they reported that neutron bombardment of uranium resulted in nuclear fission, the splitting of the uranium atom. Before this, it was thought impossible to break an atom into smaller pieces, other than just taking electrons off or something. But this was actually breaking a uranium atom, changing uranium into a different element. And that's called nuclear fission, when you take a large atom and break it into smaller ones. So the uranium atom split into barium and krypton atoms, and it also released 3 neutrons and tremendous amounts of energy. This is uranium-235 that will do this, which is less than 1% of the regular mixture of uranium isotopes. Uranium-238 is the most common isotope. It does not undergo fission. You can bombard it with neutrons, nothing's going to happen. But uranium-235, throw neutrons at it. It'll break into 2 smaller atoms and release energy and neutrons. It was a neutron that started this, and so these 3 neutrons that are emitted have the potential to start another fission reaction. So here's an example of that. This is called a chain reaction, where you get this one going, and it gives off neutrons that can start 3 more reactions, and then each of those could conceivably start 3 more reactions. And this can get big really fast. So if there's enough uranium-235 in the sample, you can get a chain reaction where it's self-sustaining, it'll keep going. In order for you to have that self-sustaining reaction, you need a critical mass of uranium-235. If you don't have enough uranium-235, you can do fission, but it will not just keep going on its own. If you get a critical mass, it'll keep going on its own, and it will explode. It'll be an atomic bomb. Yeah.
What is a critical mass?
Critical mass is enough of the uranium-235 that once you begin the fission, it will continue on its own. It'll be self-sustaining.
So you need enough to produce the chain reaction, because if you don't have enough, then
Right, because if you had pure uranium-235, obviously they would all undergo reactions. But normal uranium is less than 1% 235. So when these neutrons are emitted, if they don't run into another uranium-235 nucleus, then nothing's going to come of them, right?
Yeah.
So how much uranium-235 is in the sample affects whether it'll continue or not. Yeah.
Why can't these neutrons run into, I guess, something like a different type of atom and kind of split those and change those?
Well, they can run into other atoms, But most atoms will not undergo fission just by being bombarded by a neutron. Like uranium-238 won't do it. So only some of them will do this.
This would be like kind of like unstable, essentially. Is that what?
Yes, they need to be unstable. Because if it's stable and gets hit with a neutron, it's like, whatever. If it's unstable, that just literally blows it apart, right? Any other questions? So this is, around the time of World War II, and there was a fear that Nazi Germany would develop a bomb based on this principle of nuclear fission. So U.S. scientists persuaded Albert Einstein to write a letter to President Franklin. And it's actually in your book, and I think it's kind of interesting. It says, "Sir, some recent work by E. Fermi and L. Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable through the work of Joliot in France, as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type carried by boat and exploded in a port might very well destroy the whole port, together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air." And that's dated August 2nd, 1939. Albert Einstein. He was the most famous scientist at the time. So President Franklin listened to that, and in 1941 launched the Manhattan Project in New Mexico. And the goal there was to build a bomb before the Germans did. And it was successful. We built a bomb. The Germans didn't get their bomb built. So the first bomb was detonated in 1945. It had a force equivalent to 18,000 tons of dynamite. By the time we got this working, Germany had already surrendered, right? But Japan was in the war, and so we got Japan to surrender by dropping 2 bombs on Japan, killing 200,000 people. This was an interesting time in history. And this isn't a history class, so we're not going to go into all the ramifications of this, but this is chemistry playing a big part on the world stage, right? Huge impact. So obviously, fission can be used to make bombs. Is it good for anything else? Well, yeah, it is. A controlled fission reaction can be used to generate electricity. The upside of this is you don't get air pollution because this is not a combustion reaction. You're not even generating any greenhouse gases. In the United States, nuclear fission generates about 20% of our electricity, and in some countries it's up to 70%. So just to give you an idea of how much energy is stored within those atoms, if you have a pencil-sized cylinder of uranium, that could power a typical car for 20 years. So you probably have a pen or a pencil in your hand. A piece of uranium that large could keep your car going, never have to fill up with gas, for 20 years. That's a lot of energy, right? Think of this, a coal-burning power plant uses 2 million kilograms of fuel to generate the same power as 50 kilograms of fuel generates in a nuclear plant. Much more efficient, much more efficient. how does a nuclear power plant work? So what we have in here is the reactor. In the reactor, you have fuel rods and you have control rods. So the fuel rods are enriched uranium. It's got a higher than normal amount of uranium-235. And then the control rods, they're typically something like graphite or something that can absorb neutrons. And you can put those down among the fuel rods or pull them out. So you can use that to control the reaction. Because you don't want to start this reaction and then have the chain reaction explode on you, right? So the control rods, you stick those in, and they're just going to absorb the neutrons and stop things, okay? So this is generating a tremendous amount of energy, a lot of heat, and so we send that heat where we can generate steam. So we're using water, pumping water through here, we're heating water and causing steam. The steam is what turns the turbines in the generator and generates the electricity. So the electricity generation part is the same idea as windmills. Yeah, there's something fancier that they're called. Turbines, yes. It's the same as this. It's a wind turbine or it's been a long semester. Hydroelectric, thank you. You guys just want to get up here and do this for me? Hydroelectric, where you use water to turn the turbines and generate the electricity. But here we're using the energy from a nuclear reaction to generate heat, making the steam. And a coal-burning power plant does much the same thing, but you're burning coal to create the steam.
So what are the products from these reactions? Is it just like...
So yeah, that's a good question. What are the products here? Well, krypton and uranium and barium, for one. You do get waste. You're just not throwing gases into the air like you do with coal. But that's one of the drawbacks of nuclear power, is what do you do with the waste? The waste is radioactive. And so, yeah, we'll talk about Japan. So any questions about how the power plant works? This is a picture of a real one. I don't think I'm going to test you on the workings of a nuclear power plant. I think a lot of this stuff is good just to have heard about, so that you just have a better idea of what's going on in the world. Because it's not immediately obvious. How do you use something that could make a bomb? How can you use that to make electricity, right? So another problem, of course, is accidents. This is a picture of Chernobyl. It was in the Soviet Union, 1986. They were doing an experiment designed to reduce maintenance costs, and the results were disastrous. In order to run the experiment, they needed to disable several of the safety features that were in place to prevent accidents. The nuclear core was partly composed of graphite, which is flammable, and when it overheated, it began to burn. And that's when things really got out of hand. So there were 31 immediate deaths from this accident, and a 32-kilometer radius area became uninhabitable. So circle 32 kilometers around this. It's just nobody can live there anymore.
That was permanent?
Is that permanent? I don't know. Not like forever, but for lifetimes, probably. Because a lot of the things that are emitted from this are radioactive, and they have very long half-lives. And so they're going to stick around for a long time. So Yeah, I don't know the details of that, but it's bad. Another famous nuclear power accident happened in Fukushima, Japan in 2011, and you guys probably have heard about that. So there was a huge earthquake, a 9.0 magnitude earthquake, and the power plant went through that just fine, but it created a tsunami. And the tsunami came, and you've probably seen footage of that on YouTube. It was just mind-boggling. It was like, epic movie kind of stuff, but it was real life. This huge wave comes in and just wipes out all kinds of things. Well, it didn't wipe out the power plant, but it did flood the cooling ponds. And so they lost, they had 3 of the nuclear cores overheat and experience partial meltdowns. They did not explode. It's not in your book, but what I remember reading about this is that one of the biggest issue was they had backup generators because, most of Japan lost power. They had backup generators to run the pumps that put the cool water in to cool the reactions. But it got flooded, and all of this very dirty flood water got in there and clogged up the pumps. And so then the pumps can't work, and then the cooling isn't working. And so they experienced partial meltdown of 3 of the nuclear cores. Now, there was significant radiation release, but it was much lower at Chernobyl, and there were actually no radioactivity-related deaths that were reported. So, yes, a serious accident, but the results were much less disastrous than in Chernobyl. It's important to note that neither of these incidents was a nuclear detonation. The fuel used in nuclear power plants is not sufficiently enriched in uranium-235 to produce detonation. It can't happen. It's just not possible. U.S. nuclear plants have additional safety features to prevent accidents such as this. And that accident in Japan, that was just a really freak thing that happened. Any questions? The other major problem is disposal of nuclear waste. The amount of fuel is small, much, 50 kilograms compared to 2 million kilograms. But some of the products are radioactive and they have long half-lives, and so you can't just put them anywhere. Yes?
I was watching a documentary recently that was talking about nuclear plants and
Mhm.
how there are a whole bunch of new startup companies within the United States that are trying to take that nuclear waste and reuse it into energy, and I guess they've found a way to do it.
Cool. So, saw a documentary where some startup companies are discovering ways to take the waste from nuclear power plants and use that in different ways to generate power. So, human ingenuity. You got a problem, you got this stuff. Sometimes you can use garbage for good things, right? Currently, in the United States, the nuclear waste that's generated is just stored at the nuclear power plant. They were working on the single permanent disposal site in Nevada, but that got stopped in 2010, and there's been a bunch of committees that have made recommendations, but no decisions have been made yet, and here it is 8 years later, and still just nothing going on. That's bureaucracy for you.